So hello class and welcome to this session. So this is design of steel structures. I'm Engineer Ronjan R. Garvey. So today we'll have the lesson staggered fasteners. So in steel connections, staggered fasteners are also implemented or placed in the connection on the following reasons. In here, bolts are arranged in a staggered manner because, first, if there will be an even number of bolt requirement, of course, there's no symmetry on the bolt requirement, okay, on the configuration, because the number or quantity will be in odd number. Secondly, there will be space limitations on a lap length A, or this is what we call L, or the connection length. So another condition on staggered fasteners, if your member is inclined or in the configuration like this, of course you're going to connect that member parallel to the loading. Hence, the configuration requires that your bolt should be in staggered form. So the second condition, of course, you need to make your bolt or connections parallel to the loading. In that case, it depends on the configuration of the connection. Now, on staggered fasteners, fracture along the inclined path where the influence of an offset hole may be felt on the nearby cross-section. So it will develop two stresses here, namely the shear stress and the axial stress on the section. So there will be a developed fracture connecting the staggered formation. So this will be the root of the fracture. Of course, the first section to fracture is the section nearby your loading. Therefore, your actual formula that sigma is equal to P all over A can no longer be applied for the inclined section at BC, B to C. So again, because there will be a combined stresses here, namely the tensile and the shearing stress. So, to account this in the calculation, we deduct the corresponding area of the staggered hole D prime. So it is suggested that D prime will be equal to the bolt diameter less S squared, or the square of the pitch of the bolt all over 4G. So S is the stagger or pitch of the bolts. Say this is the S, and G is the bolt transverse spacing, or what we call the gauge distance. Hence, your net width will be equal to your gross width less the summation of this D prime. Now, on D prime, the expression S squared all over 4G could not be present in your equation in some situations. So Wn is the net width, Wg is the gross width. So therefore, the net width of that cross section will be equal to the gross width less the sum of the expression d minus s squared all over 4g, or that is the d prime. So the clue here is that we determine a root, say a, b, c, d, and then work from top to bottom, and then go over for the bolt one by one. Say we have here the first bolt, b, at the topmost root. So let us look where it come from. So it came from letter A, the root A. Hence, connecting that to your root A, we have a vertical line. So if there will be a vertical line, therefore, there will be no stagger. Hence, in your equation d prime, this is not applicable. So therefore, there will be no pitch or stagger pitch. So what is left on the equation is the summation of the diameter of bolt. So moving on to bolt C. So we are through with bolt B. Of course, same procedure. Let us take a look at where it comes from the top. Of course, it comes from B on the root. So connecting the bolt to bolt, we will have a diagonal. So the diagonal implies that there will be a stagger or pitch of the bolts. Hence, this will be applied, okay, on the equation, as well and on at this equation. So there will be pitch, so therefore that implies that we have the whole equation to work with. So there will be a gauge distance as well as the pitch. Again, the diagonal implies that there will be S, or stagger or pitch of the bolts. Then we emphasize that d prime shall be calculated through this formula. So let us have an example. So in here, compute the smallest net area for the plate shown in the figure. The holes are for 1 inch diameter bolts. So here is the configuration. First things first, we need to compute the effective area of the space occupied by the bolt. Of course, it's mandated that we add 1/8 to your diameter, and that will be the effective or the nominal area for the bolt, and that will yield to 1.125. So next, we are going to have the root, okay, the possible root in the configuration near to your loading. So for root A, B, C, D, E, we apply this formula that the net width is equal to the gross width less the summation of d primes. Hence, we have here equation. So the net width is equal to 16 minus 1.125, or the diameter, minus that equation, 3 squared all over 4g. If you notice, there will be two of them. We'll be having the pitch, okay, this one. So if there is diagonal, there will be a pitch, okay, equal to 3 inches, and the gauge distance of 5. We also have here another one, so there will be 2. That is why 2 is being multiplied here. Okay, so therefore, we will come up with a value of 13.52 inches. Next, we consider another root, say ABDE. So in here, there will be no diagonal to observe, so therefore there will be no pitch, meaning there is no staggered formation on that root ABDE. So still, we use this formula and just simply neglect this one because there will be no pitch. Pitch is equal to 0. So in that case, again, we'll compute for the net width or the gross width minus the diameter of bolt, 1.125. There will be 2 of them, okay, 2 bolts. So therefore, the net width here will be equal to 13.75 inch. Now, comparing root ABDE and the root ABCDE, of course, we will consider here the lesser value of the net width, which is equal to 13.52 inches. Now, knowing that one, we'll just have to multiply that by the thickness to get the area. Hence, the net width times the thickness will be the net area. So the required net area will be equal to 13.52 multiplied by the thickness of 3/4, or that is 0.75 inches. Hence, we will arrive the net area 10.10 square inches. Okay, that's it for the problem. Next problem. Determine the smallest area, the net area, for the American Standard channel shown in figure. The holes are for 5/8 inch diameter bolts. So here's the configuration. Take note that the connection is on the web. Okay, so the web or the stem of the channel. So first things first, again, we're going to compute for the nominal bolt area by adding 1/8 to your 5/8 inches diameter bolt. So we will arrive at a value of 0.75 inches. The next step, of course, is to come up with the root starting at the nearby cross section on the loading. So we have here ABE for root ABE. Now, before we can proceed here, we need to determine some properties of your channel. So that channel is actually C6 by 13. Therefore, we will be having an area equivalent to 3.81 square inches. We also need the thickness of the web, because we have noted that the connection is within the web. In a while, we will discuss an example that involves a connection on the flanges also. So in this case, we are only concerned with the area and the thickness of the web, since we have no connections on the flanges element of this channel. So the gross area for the channel will be 3.81 square inches. So in this case, we can no longer work with the width. Instead, we will work for the net area. So we will note also the web thickness of 0.47 inches. So again, we will work with the net area instead of your net width, because on the first problem, we know the net width, but this time, what we know is the gross area. So we'll just have to note that your net area is just equal to the net width times the involved thickness. So we will come up with this formula that A sub n is equal to the gross width. So the gross width minus the summation of d prime, just the same. Of course, this is the formula for the net width actually a while ago. Of course, in here we shall distribute your thickness in the equation, and then take note that this product is your gross area. Now we can now express the net area in terms of the gross area minus the summation of d prime times the thickness. So next is, we now express the WG or gross width times thickness through AG or the gross area minus the summation of d prime times the thickness, because we can bring out thickness, okay, summation of t times d prime. So again, this is just an expansion of your net width, and the net width is just simply equal to net width times thickness, or the net area is equal to net width times the thickness, so that we can express the net or the gross area in our equation. Now, the thickness here could be the web thickness or the flange thickness, depending on what is on the location of your bolt. So if your bolt is within the web, then use the web thickness, and if your bolt or the connection is in the flanges, you can use the flange thickness. So moving forward to the problem, we have now computed the nominal bolt area of nominal bolt width of 0.75 inches. So we will consider the root ABE. In the root ABE, we can find no diagonal or pitch on the root. So AG is 3.81 here. So we can just cancel that expression. S is equal to 0, or the pitch is equal to 0. So what is left is the web thickness. Now, web thickness because your bolt is on the web. So we less the thickness of that web, or actually this is the diameter, 0.75. and the thickness is 0.437 on the table a while ago. And you can come up with a net area of 3.48 inches. So the next possible route is A, B, C, D. So we consider this route. So in here, you can have this equation that AN is equal to, we have the gross area. Gross area is always present in your net area. Of course, the summation now would include the bolt at B with this equation. Again, the thickness is on the web, and the bolt area C here, so that we come up with the summation. So on bolt B, it is obvious that bolt B come from A, and that will be a straight line. If that will be a straight line, therefore S squared all over 4G, there will be no pitch, so that will just be neglected on the equation. So we can now compute. We place here the 3.48, which is actually this one, was computed a while ago, 3.48, and then we less this expression. The diameter is 0.75, the thickness is 0.437 for the web. Now we have here a positive sign because negative sign will just be distributed on the inner equation, and the second term will become positive. So take note of that. So this time, this is bolt C, and bolt C come from bolt B. There will be a diagonal configuration, which means there will be an S value, or the spacing will be 2 inches, and the gauge length is 3 inches. So again, we multiply that by the thickness. So therefore, the net area will be equal to 3.3 square inches. So this will be considered because this will be the least net area from the possible route we have calculated. So this will be the answer. Now there are some cases that the connection will be found on different elements. I mean, it can be found on the web, and it can be found on the flanges. Let us say we have here a channel of web thickness. So in here you can see that there will be reinforcement or connection on the flanges and the web itself. So we'll just have to label the gauge distance of this bolt from your flange element. We also label your bolt distance up to the corner, from the center of the bolt up to the corner, and consider folding your flange. So what we do, so if this is the label G1 a while ago, we'll just have to place it here. Say this is G1, okay, and this will be G. So we'll just place it here. So we'll just have to fold that one or rotate it vertically, and notice that there will be a space here, and that space here is actually the gap or the overlap between G and G1. Now, this dimension is actually the web thickness. Okay? So that is actually the web thickness. So therefore, when we are concerned with a channel having a connection on web and the flanges, we will treat your gauge spacing with this equation, or the gauge distance is given by the equation G, okay, G plus G1 minus the web thickness. So if we have an S shape or an I-beam here, of course, just the same, we will be having a label for G and G1. These are the distances from the corner. So in a moment, we will fold those flange elements to have the configuration. Okay, so again, we have here a connection on the flange and the connection on the web. Okay. What we do here is to consider the half of the thickness of the web, because in this channel, we will be folding two elements of your flanges at the top to make it vertical with that of your web. So we do the same. We'll just have to label this or shade this portion and place it here. This is G1, and this element shall be folded. Okay, if this is G, this is the half of G. So notice that there will be small space here on white, okay, and all of those elements will be folded vertically. So again, you can found here 1/2 of G, and this small element here will be 1/2 of your web thickness. That is why on the S shape or I-beam here, we will treat the gauge distance to be equal to this equation. G over 2 plus G1 minus web thickness all over 2. Okay. So let us consider that in an example. So find the available strength of the S shape shown in figure. Now the holes are for 3/4 inch diameter bolts. We use A36 steel shape. So here will be the illustration. We have the given center to center diameter or center to center spacing of your bolts. Now the bolts can be found on the web and the flanges of this S shape. So the S shape is S15 by 50. So here is the configuration. So first things first, we need to look at the table on its properties. That is S15 by 50. So we have the area equal to 14.7 square inches. So we also need the value for the web thickness, that is 0.55 inches. And this time, we will consider the flange thickness since there are connections on flanges. 0.622. So we take note of AG 14.7, thickness of the web 0.55, the flange thickness is 0.622 inches. Now we also go back to our data on A36 steel, wherein Fy for yielding 36 KSI and for fracture by Fu is equal to 58 KSI. So knowing those properties, we can now start calculating. The first root will be A to D, and that will be a straight line, take note. So we use this equation. So in this equation, so if we have bolts on flanges, so all bolts will be on the same file. So therefore, that bolt will be just transferred here, okay, in the calculation. So that is the technique here. Okay, from here, we are going to transfer it on the first root. Only those bolts on the flanges. Likewise, the bolt on the flange on the bottom portion, we'll transfer it in here. Okay. So we start our calculation. So first things first, we add 1/8 to your diameter, 3/4, and that would yield 2.875 inches. So for root AD, again, this is the equation. Your thickness here could be on the flange or the web. So in this case, we'll consider the web thickness, or the flange thickness, I should say, because the connections are on the flanges. Now, there will be no pitch obviously on the root AD. So we'll just calculate. The gross area for the channel, or the S shape, is 14.7 minus 4, why 4? Because there are 4 bolts on the flanges. That is why I've emphasized that we transfer all of the bolt on the same root within the flanges. Okay? So 0.875 is the diameter, and then 0.622 is the thickness of your flange. Okay, and this shall yield to 12.52 square inches. That is the net area when we consider the root A to D. For root ABCD, again, this is our equation. So this time, obviously, there will be a gauge distance because we can find a pitch along the root. So of course, the equation is given by G over 2 plus G1 minus the web thickness all over 2. So half of G, we have 3.5 all over 2 plus your G1 is 2.75, or that is 2 3/4 in the figure, minus the web thickness is 0.55, so get the half of that. So therefore, with the calculation, we'll come up with 4.225 inches. Now this shall be used on the calculation of D prime, which involved S and G. Now going back to this equation, we take this root. So AN, we first start with your bolt A, and your bolt A, where it come from, so no bolt yet, so therefore that is assumed to be a vertical line. So when there is a vertical line, there will be no pitch yet. So we have, again, this is AG, minus, there will be 2 bolts on bolt on A. 0.875 is actually the bolt diameter times the thickness of the flange. Again, this is flange thickness because we are on point A. Point A is within the flange. Hence, we use the flange thickness. So, moving on to bolt B, of course, when we connect that to your bolt A, there will be a diagonal and therefore there will be a stagger. Hence, we have S, or the pitch distance. So, we less that one. So, this time, the thickness is 0.55. There will be a single bolt. So, there will be only single bolt here. 0.55 again is the web thickness because the bolt is within your web this time. So we calculate the D prime. So D prime is D minus S squared all over 4G. Our D is 0.875 minus that expression. So the pitch is 1.5 and the gauge distance computed is 4.225. So moving on to bolt C, from bolt B to bolt C, there will be a vertical connection within. Therefore, there will be no D prime here or pitch. There will be no pitch. There will be no D prime. Hence, we will just consider the product of your bolt diameter times the thickness of the web, 0.55. So again, 0.55 because bolt C is still within your web. So moving on to point D. Again, we less that one. There are 2 bolts with the flange thickness. Now, point D, the bolt at D is on the flange. So we use the flange thickness 0.622. And this expression, because connecting C to D, there will be a pitch of 1.5. So you just have to expand that equation. 1.5 squared all over 4 times your gauge distance, 4.225. So we calculate the net area to be equal to 11.73 inches. Now take note that our requirement on this problem is actually the available strength of the S shape. So we are quite familiar in computation of the available strength if we know the effective area. So at this moment, we are going to choose between the root AD and root ABCD of the net area. So between those two, net area, the derived net area between those two roots, we will consider the smallest or the least net area. Hence, we have 11.73 square inches. So with that, we can take this as our effective area in the calculation of the available strength. Of course, what we do next is to compute the nominal load P sub n. Now for yielding, we just have to pair Fy to Ag. Okay, Fy for A36 steel is 36 multiplied by the gross area, 14.7. So we will come up with a value of P sub n is equal to 529.2, or the nominal load. Now for fracture, we calculate Pn by pairing your Fu times the effective area. So Fu for 836 steel is 58, and your area. So this is where we can now utilize what we have computed, 11.73, and the product would yield to 680.3 kips. Now using the load resistance factor design, you just have to multiply a resistance factor of 0.9 for yielding. So phi Pn, or the design load, the design strength will be 90% of 529.2, and that will be equal to 476.28. So we do the same for fracture using LRFD. We have the resistance factor of 0.75 for fracture. So we get 0.75 of the nominal loading, the nominal strength, 680.3, and that will be equal to 510.23 kips. Okay. So between the two, of course, we choose the lowest or the least. So therefore, by using LRFD, the allowable strength or the design strength, okay, LRFD, the term is the design strength, is from yielding or yielding controls on LRFD. Now using the allowable strength design, the allowable strength will just have to multiply 0.6 to FYAG. So 0.6 of 529.2, that would yield to 317.52 kips. So we do the same for fracture. The allowable strength for fracture for ASD is 0.5 FY. Sorry, so this should be FUAE. So we multiply 0.5 by FUAE. So 0.5 times 680.3, and that will be equal to 340.50. So using ASD again, the list is 372.15, which means that using ASD, allowable strength, the yielding controls. Okay, so that ends our session for today. Thank you and have a nice day, class.